But what we're going to be discussing is how antiderivatives, now I know it sounds like a big word. Anti means what? If you are anti-Trump, for example, what does that mean? You're against, or you're not for something. So it's, in other words, it's the opposite. An antiderivative is going to be the opposite of finding a derivative. Now, to put this in perspective, let me kind of show you, hopefully something that you can relate this to that would make sense. You guys remember when you first started algebra years ago? And before you learned how to factor, you had to learn how to use FOIL. For example, if you had x plus 2 times x minus 3, and you were supposed to multiply those together, you learned FOIL. First, outer, inner, last, right? And then once you had distributed, because that's all FOIL is a way to organize using the distributive property, then you were able to simplify, and this turned into something like this: x squared minus x minus 6. Those would be all the terms once that thing has been distributed. But then, after probably a year or so of working on using FOIL and multiplying out binomials, 2 terms inside each parenthesis, this is the part that many of you kind of decided, I am not a fan of algebra. You had to go the opposite direction. You were given a polynomial, something that looked like that, and the instruction changed from multiply this together to factor, okay? And that's probably where many of you decided that you did not like the F word, okay? And the factoring part was a little more uncomfortable for most people as opposed to using FOIL. FOIL, you seem to have an easier time keeping up with the process. The going backwards, even though it's just undoing FOIL, it's the idea that you have to think opposite. Make sense? Okay, so an antiderivative is simply this. We're going to be going the opposite direction. Okay, let's review for a second. If I gave you a function and I asked you to find the derivative, what information is the derivative telling you? You remember? We use the derivative to find what at any point on that function? The slope. It's a rate of change, okay? The derivative will tell me a function I can use to find the rate of change on any point on that function. So it's useful, it's helpful, because we already know there's a lot of business applications that go with that. The issue with needing to go backwards is this. Antiderivatives or integrals mean we know something about how this function has been changing, but we want to go back and find, well, what was the function? Because if we were able to get the area under the curve, if we knew, if we could see what that graph looked like, and we needed to find what the area between the x-axis and that curve would be, that's what integration is, or antiderivatives. It lets us go backwards to find what was the original function when I know what the rate of change is. Okay, so in that respect, it's kind of the same principle as FOIL and factoring. We're going to be taking that derivative and figuring out what gave us the derivative to start with. Now, symbolically, here's where you know what it is they're asking you to do. We already know if we're finding a derivative, we have that little apostrophe that's a prime, right? So if we're looking for a derivative, then it's going to say find, and we're going to have maybe a lowercase f with that apostrophe, which means prime, and it would be find f prime of x. That's what tells us to find the derivative. When we're going backwards, we're going to use a capital letter instead of a lowercase letter. All right? So we would start with a function that was actually the derivative, and to find the original, we'll be finding big F of x, okay? So let me show you what the rules are when you're going backwards and you want to find the antiderivative or the integral. Now I apologize that, as I said, the formatting messed up going into my iPad, but you have it printed out where you can see it better on your paper. This little goofball thing in front of the x to the n is, if I can get it to write, I don't think it's going to write on there. Okay, we'll just write it over here. All right, it looks like sort of a relaxed S, and that is the symbol for an integral. So if we want to integrate something, a variable x raised to some number power, that's what the n is. And the way we know this thing was a derivative is we see that dx afterward, okay? That was our variable of that was used in the derivative process, so we're going to call it the variable of integration since we're going to be going backwards. You will see a dx after your function when you were trying to integrate. And all this means is, tell me, if I had this and I wanted to find the derivative, how do I get the derivative when I have, say, x to the third power? You remember? To differentiate, what do I do to the exponent? I take away 1, right? I pull the exponent down, multiply it in front, and I take away 1 from the exponent. That's what we did when we differentiated. Well, guess what? If I'm going to integrate, instead of taking 1 away from the exponent, guess what I'll do? Add 1. Exactly. This is going to integrate as x to the n plus 1 power, and then we have to divide by the new exponent, n plus 1. Okay? Now, there is one little rule. This says n cannot equal negative 1. Okay? And that's important because if I'm starting off with an exponent of negative 1, what's going to happen when I add 1 to negative 1? I get, oh my goodness. And if I have x to the 0 power, I've lost the x, right? Because x, anything to the 0 power is equal to what? Just the number 1. So I can't integrate using this pattern. If my exponent is a negative 1, we're going to learn a different pattern to use. But if it's any other number on the exponent, doesn't matter if it's positive, doesn't matter if it's negative, I will simply keep the x, I add 1 to the power in the exponent. If I have a coefficient in front of this, we're going to see in a minute, we just keep it. We never lose those coefficients or those scalars. And then the only other thing that's new is we divide by the new exponent. Okay? So that's pattern number 1. Pattern number 2 is very simple. If I have e to the x power, and that's what I want to integrate, let's see if you guys remember when we differentiate e to the x, what do we get back? The same thing. So if we integrate e to the x, we will also get back e to the x. So that's not a new one. That one is one, and by the way, just to verify this, wouldn't it make sense, sort of like when we learned to factor, to check ourselves to be sure we did it right, couldn't we use FOIL to multiply our factored form back together to be sure it gave us what we started with? Well, don't you think to check our integration, we ought to be able to differentiate our answer and see if it gives us what we started with? We're going to be able to do that too. So you've got a built-in checking system. Since we already know how to differentiate, we're probably a little more comfortable with that. After we try to integrate something, take that answer, differentiate it, and see if you get what you started with. And we'll practice that in just a little bit. Okay? Now, there's one more pattern we want to be sure we talk about, and this is what we need if our x was to the negative 1 power. Remember, we couldn't use this first rule if our exponent was a negative 1. So if our exponent is a negative 1, it means that we would have x in the denominator, right? Something like 1 over x dx. And I could have something else in the numerator, a different number than 1, like a 2 or a 3. We'll talk about that constant in a minute. But if I tried to take that x out of the denominator, write it with a negative exponent, it's going to be x to the negative 1. So here's how this one integrates. If it has an exponent of negative 1 or it's x to the positive 1 in the denominator, it will integrate as the natural log of x. And because with a natural log, or any log for that matter, what follows, it has to be a positive number. We have to be sure we use absolute value bars around the x. Now, think for a second. Remember I said we can always differentiate to double check ourselves. Did we learn a differentiating pattern for the natural log of x? What does it differentiate as? 1 over x. It's always 1 over what you were taking the natural log of. So these two, 2 and 3, should be easy in the sense that they already fit the patterns we've been used to from differentiating. And then we've got an adjustment now that we can make on something that's polynomial when we have x raised to some power. Now, all that 4 and 5 are telling us is that some of the same rules we got to use when we were differentiating apply with integration. If you look at number 4, it's the constant multiple rule. It simply says if I'm trying to integrate and there is some constant value, we'll call it k, times our function, before we integrate, we can kick out the constant because it has to stay, and then we'll just integrate whatever our function is. So it won't matter if it's a natural log, if it's exponential, if it's polynomial. If there is a number in front of our function that's being multiplied times that, we can kick it out and just keep it, and it'll get multiplied by whatever we get after we integrate the function. The other rule that's very important just reminds us if we are trying to integrate a function plus another function or a function minus another function, just like we could differentiate term by term, we can integrate term by term. And I realize that it's a scribbly mess on my sheet that you're seeing on the screen, but it is written out correctly on yours. So, you ready to give this a shot and see what happens if we try a little integration? Notice it says you're going to find each indefinite integral and then check by differentiating. We already said we can double check our work if we take the derivative and see if it gives us back what we started with. So we are integrating 12x dx, all right? The dx is there to tell us our variable of integration is x. It also indicates this is a derivative function. We want to go back to what the original was that would have differentiated to give us the 12x. So let's see if we can apply these rules. Do you see a constant that is being multiplied times x? It's what? What's the number in front of the x? 12. Our rule number 4 up there said, if I have a constant that's being multiplied times my function that has x in it, I can kick it out. So this is going to be the same thing as 12 times the indefinite integral of x dx. Now, what is the exponent on the x, even though I don't see it?
1.
It's a 1. And what did the rule tell us we're supposed to do when we're integrating? Add 1. So my 12 is still there. When I integrate x, and by the way, when I'm actually doing the integration part, that's when I drop off that relaxed s, the integral sign. And this will become x to the 1 is already, the exponent is there, and I've got to add 1 to it. So I'm going to have 12 times x to the 1 plus 1 power, but then I have to do what? Divide by my new exponent. And what's my new exponent? 1 plus 1 is 2. Does that make sense? We kept the 12, because it's a constant multiple or a scalar. And then we added 1 to the exponent we started with. 1 plus 1 is 2. And then we divided by the new exponent. Now, if I clean this up, I can reduce down 12 divided by 2. What is that? 6 times x to the, what's my new exponent? Second power, x squared. Now, how could I make sure this thing has been integrated correctly? Try to differentiate. What would you get if you differentiate 6x squared?
12x.
That's all there is to it. Okay, now that was a single term. That was very simple. And I have one more thing I need to point out to you that I didn't mention when we went through the rules, because I wanted us to get through an example problem of how to integrate before I talk to you about one of the names that you see at the heading of this lesson, besides antiderivatives, is indefinite integrals. Now, here's what makes an integral an indefinite integral, okay? It means I'm looking for the family of integrals. And when I say that, I want you to think with me for a second. If, and let me get a little space here where I can write and just show you. Let's say we had started off with our original function being 6x squared plus 4. And I ask you to differentiate that. If you differentiated that, what would you get? 12x. What if you had started off with 6x squared minus 9? If you differentiate that, what would you get?
12x.
Okay, so do you get the idea that I could have any number added or subtracted at the end of this, and it would still differentiate to give me 6x squared? That means when I'm integrating and I'm finding the family of functions that would be able to give me 12x as the derivative, okay, then that means there's a lot of different options, because I could have plus any number or minus any number at the end of that function. So what we do to indicate this is an indefinite integral, that there is a family of functions that would give us this, is after we get this thing integrated, we put a plus c. And that c simply means I could add any constant to the end, and if this thing gets differentiated, it's still going to give me back 12x. Okay? So if it's indefinite, that means it came from a family, and we will have a plus c at the end. All right, let's try another example. We have the indefinite integral of 9x to the 1/2 power dx. All right, so tell me, do you think we could integrate this? I think so. Do you see a scalar or a constant multiple in the front? 9. So I have to keep that. I'm going to write down the 9. And then I'm integrating x to the 1/2 power dx. Now, to integrate that, it means I'm going to do what to my exponent? Add 1. Now, the problem is it's a fraction. So when I go to add 1, I need a common denominator. What's going to be my common denominator? 2. So I'm going to add 2 over 2, and that's going to give me what for my new exponent? 3 over 2. Now here's where you got to be careful. We're not done with the integration yet, are we? Because that's my new exponent. What else do I have to do with the new exponent? Divide by it. So if I put this over 3 over 2, now it looks like a huge mess. So what am I going to need to do to clean this thing up? Dividing by a fraction is the same as what? Multiplying by the reciprocal. There you go. So if I'm trying to divide by 3 over 2, isn't that the same as multiplying by 2 over 3? That's all we're doing, is instead of leaving it as a division problem that has a fraction in it, we're going to multiply by the reciprocal of the denominator. Now, that means this first factor I could put over 1, so it looks like a fraction times a fraction. Do you see anything we could clean up? Yeah. 3 and 9 have a common factor of 3, so 3 goes into 3 once, 3 goes into 9 3 times, and now if I multiply together the parts that I would have the 3 here times the 2 here, and 3 times 2 is what? 6x to the 3/2 power. Right? Am I done? Because I got to write what else?
Plus C.
Excellent. Plus C. Now, how could we be sure we really got this thing integrated correctly? Let's differentiate and see what happens. If we were to take 6x to the 3/2 plus C and we differentiated, it means I would have 3/2, because I pull that down, multiply it times 6x, and my exponent goes from being 3/2 to what? 1/2, because I take away 1, so it's like minus 2 over 2. And if I were to clean this up, 2 would go into 6 3 times. 3 times 3 is 9, and I would have 9x to the 1/2 power. It checks. Got it? All right. Let's look at another example. Oops. Okay. So number 3 is integrating 2e to the x power dx. How's that going to integrate? Is there anything we can kick out?
2.
Kick out the 2, and then it means we're integrating e to the x dx. How do you integrate e to the x? It's just e to the x. This is going to be 2 e to the x, am I done? Plus c, right? Sometimes that's all there is to it. That was very simple. And again, if we differentiate, we can tell that's going to give us back what we started with. All right. Here's another one, and instead of using that integral sign, it just simply says find all the antiderivatives for dy over dz, and that is simply another way of saying that we are differentiating with respect to whatever the letter is that follows d in the denominator. So this would be as if the original function, or the function that we're trying to integrate, was y equals 3z to the -1 and plus 7 on the end. Okay? And so what we're trying to do is integrate that. So if we put the integral sign down, because that's what it's telling us we're going to need to do, I need to take this function that they've given us, which is 3 times z to the -1 power plus 7, and then we need a dz after it, because that's our variable of integration. All right? We are going to be integrating with respect to the variable z. Now, I see more than one term here. This is the first time they've given us an example that wasn't just one term. So how do we integrate those? It's what? Excellent. You identified it. The problem is with an exponent of -1, I can't add 1 to the exponent and integrate that way. Instead, I've got to recognize this would be the same thing as, and I'm going to rewrite it to see if this looks a little bit more familiar, 3 times 1 over z. That would be the first term we're going to integrate, plus Our second term is 7 dz. Because we're going to integrate term by term. So I'm going to separate this out. Just not that you have to write it down this way. I just want you to see what we're doing. And if I look at that first term by writing it this way, where I see the 1 over z, that's the same thing as the 1 over x. And how does that integrate? That's a natural log. So because the 3 is a scalar, we keep it, it comes out. We integrate 1 over z as the natural log of z, and that's got to be the absolute value of z because we said whatever follows a logarithm or a natural log has to be a positive number. And now we're ready to integrate the second term. So I've got my plus sign. How do you integrate 7? It becomes what?
7z.
It becomes 7z. Very good. Remember, think about the fact I don't even see a z there. Why do I not see a z there? It's because it's actually z to the, what would be my exponent? If I don't see the z, it's because the exponent is 0, right? What I'm saying is when we're integrating this, this is the same thing as 7 times z to the 0 power, isn't it? That's what 7 is. If I add 1 to that exponent, that's how I end up with z to the first. Okay? So if it's a constant, just like if I had 7x and I differentiate it and it becomes 7, if I'm integrating and I see a constant, it's going to integrate as that number times your variable. Okay? But that's why. Because really, when I don't see the variable, it's because the variable had an exponent of 0. And if I add 1 to that exponent, that's why it's going to show up when I've integrated. So I get 3 times the natural log of the absolute value of z plus 7z, what goes at the end? Because it says find all the antiderivatives, I need a what? Plus c. Now, let's review again. How can we double check to be sure we've done this correctly? Take the derivative. All right, so if we were going to differentiate this, I know I keep the 3. What's the derivative of the natural log of z? Oh, come on. How do you, okay, it would be 1 over my variable. So 1 over z plus, how do I differentiate 7z? It becomes 7. So if I wanted to clean this up a little bit, instead of leaving it as 3 times 1 over z, and I'm trying to see, would it be the same thing I started with, couldn't I write that as 3z to the negative 1 plus 7? That's how I know it's right. Okay? You can always differentiate your answer to see if it gives you back what you started with. Now, on one like number 5, if we were differentiating the way that it's written, we would need to use what rule? Do you recognize? Well, this would be the product rule, wouldn't it? Because I've got x to the third times, I've got 3 terms in a parentheses. Now, we said when we did that, we had a choice. You could use the product rule and then do the algebra after you do the calculus, or you could do the algebra first. Could I distribute and get rid of the parentheses? And if I do that, then it's going to be easy to integrate. If I don't distribute first, I don't have a backwards product rule for integration. I'm going to have trouble. But I can distribute this and multiply everything in the parentheses by x to the third. So let's do that to get started and see what we have. So I'm going to have the indefinite integral of, what's going to be x to the third times x squared? How do you multiply when bases are the same? You do what with the exponents? Add them. So x to the third times x squared becomes what? X to the fifth. Plus, what is x to the third times 2x? 2x to the fourth And then I have x to the third times negative 8, so that's minus 8x to the third. And then I still have my dx, okay? So instead of integrating one term or two terms like we just did, now we're integrating how many terms? 3. I have 3 terms, but I just integrate term by term, okay? So it's up to you. I'm going to write it where I'm integrating term by term. You don't have to put this on your paper, but you have to understand this is what you're doing. So we're going to integrate x to the 5th dx, plus we'll integrate, now the 2x to the 4th, can I kick the 2 in front? And then I'm integrating x to the 4th dx, minus, and I could do the same thing here, I could kick the 8 in front of the integral sign, and then I'm going to be integrating x to the 3rd dx. All right, let's go through term by term and integrate. What do we get if we integrate x to the 5th? X to the, because I'm adding 1 to the exponent, so 5 plus 1 becomes x to the 6th, but then I have to do what else? Divide by 6. So far, so good? Plus, what am I going to have to do in the next term? I write down the 2 and then do what? Add 1 to the exponent. So 4 plus 1 is x to the 5th over 5, the new exponent. Now I need my minus sign. Here's my 8. And how do you integrate x to the 3rd? X to the 4th, because 3 plus 1 is 4. And then divide by that new exponent, which is 4. And then I know I have a plus c at the end, right? Okay, now, if this can be cleaned up, I need to clean it up before I say I'm done. I don't think I can do anything with the first term. It's still x to the 6th over 6. Plus, I don't see anything I can do with the second term. 2x to the 5th over 5. But what can I do with the third term? Can I simplify something? What is the 8 on top and the 4 on bottom going to reduce to? Yeah, 4 goes in here 1 time, 4 goes in here 2 times, and I have a minus 2x to the 4th plus c. Now, let's make sure we have not made any mistakes. So we're going to do that by differentiating. Tell me what happens if you differentiate x to the 6th divided by 6. It becomes, and you could think of that as 1/6, and then with this, because there's a 1 in front of the x, even though I don't see it, so I could think of that as a scalar of 1/6 times x to the 6th. Now differentiate x to the 6th. That becomes what? You take away 1 from your exponent. Wouldn't that be what? Yeah, you pull down the 6 as a scalar, and that would be 6x to the 5th. And these 6's are going to cancel, and I'm going to get that x to the 5th. Plus, on this one, if I have 2/5, and then with my x to the 5th, I pull down the 5, take away 1 from the exponent, that would be x to the 4th. Is there my 2x to the 4th right there? And then I had a minus 2x to the 4th, so I still have that minus 2, but I've got to do what when I differentiate x to the 4th? Pull down the 4, and it becomes x to the what? 3rd. Is that my minus 8x to the 3rd? Checks. We did it right. Okay, do we have any questions so far? All right, let's look at a few more. So if I see a radical in my equation, just like when I was differentiating, if I'm going to be integrating, do I want to leave it in radical form? No, I'm going to have to rewrite it how? With a fraction exponent, okay? I'm probably also going to want to make sure, unless it's just an x to the first power in the denominator, if I have any other exponent on it, I'm going to want to rewrite it with a negative exponent. So I'll be able to use these integration rules. So before we integrate, we're going to need to rewrite this function. So let's see if you can tell me, how would you rewrite 3 over x squared? That could be 3 times what? Good, times x to the negative 2 power. And then I see a minus sign. And how could I rewrite the square root of x to the 5th? Well, my radicand is what's under the square root sign. It's an x. And do you remember how to turn it back into a fraction exponent? If it's the square root of x to the 5th, what's going to be that fraction exponent? The denominator has to be which number? Whatever the root or the index is. If it's a square root, what's my index? 2. So it's going to be an x raised to a power that has 2 in the denominator. What's the numerator? The power in the numerator. Yes, I keep the exponent that I already had, which is a 5. So I have 3 times x to the negative 2 power minus x to the 5/2 power, and that is what I need to integrate. So I have my dx after it. Okay, let's see if we can do this term by term. What do I do to the 3x to the negative 2 power to be able to integrate it? Keep the 3, and I do what with the exponent? If it's x to the negative 2, I add 1. So I have my negative 2, add 1 to it. That's going to give me what for my new exponent? A negative 1. And then I do what with that new exponent? Divide by it. Okay? Copy down your minus sign, and now we're going to have to integrate the x to the 5/2 power. And we're supposed to do what with that? And actually, yeah, we're supposed to do what with that exponent? We're going to have to add 1. So if we add 1, that's adding a 2 over 2, correct? Which becomes what for my exponent? That'd be 7 over 2. And then don't forget we've got a plus c at the end. Okay, let's clean this up now. Because if I have a 3 in the numerator and a negative 1 in the denominator, what's that going to turn into? Oh, come on. Positive 3 on top divided by negative 1 on bottom is a negative 3. And then I have the x to the negative 1 power, which I can either leave it as x to the negative 1, or I can write it as over x to the positive 1. Okay? That would make sense, right? Either way. Now, let's see if we can do a little cleanup on this. First of all, if I have a minus x to the 7/2 power, and it's being divided by 7 over 2, we said dividing by a fraction is the same as multiplying by the reciprocal. We want to multiply this times 2 over 7, right? So that should give us a negative 3 over x, and this minus sign times x to the 7/2 times 2/7 would be minus 2/7, and then we have x to the 7/2 and our plus c. Now, what should we do to make sure this is right? We would need to differentiate it, right? And so if we were differentiating, check and see. If I take the derivative of that, what is the derivative of negative 3 times 1 over x? Wouldn't it be a... Yes, we would want to take the x, put it in the numerator. So it would be a negative 3x to the negative 1. And that's how you would end up with the x to the negative 2, which would become an x squared on the bottom. So we would end up with, and let me rewrite that so you can see it, negative 3 x to the negative 1. To differentiate, take the negative 1, multiply it times the negative 3 that's in front of it, and that would give us a positive 3 times x to the negative 2 power, right? Which is the same thing we started with, 3 over x squared. Now on this one, where we have minus 2/7 times x to the 7/2, we would have the minus 2/7. We're going to have to multiply times the original exponent we have here, which is 7 over 2, times x to the, when I take away 1 from 7 over 2, that's like subtracting off 2 over 2, and that would be 5/2. These are going to reduce down, and I would have minus x to the 5/2 power, which if I went back to radical form would be minus square root of x to the 5th. So we can use differentiation to double check it works. Are we okay? Oh my. All right, let's look at the next one. We have 5x plus 3 divided by x to the 3rd. Now, if this were a differentiation problem, we'd have to use what rule? Quotient rule. Unless we took the x to the 3rd, moved it to the top with a negative exponent and distributed. That would be legal to do as well, wouldn't it? Do we have any rules for integration that look like backward quotient rule? Nope. So what do you think we're going to need to do? We're going to need to get rid of the fraction part. Now, you can raise this up to x to the negative 3rd power and distribute, or the other thing you can do, depending on what you're more comfortable with, you could separate this into 2 fractions, and you could write it as 5x over x to the 3rd plus 3 over x to the 3rd, but the bottom line is you're going to need to change it to a negative exponent before you integrate anyway. So why don't we just rewrite this as the indefinite integral of, we'll have our 5x plus 3 in parentheses, and we'll multiply that times x to the negative 3rd power. And that way, when we distribute, the negative exponent will already be there, and it's going to make it easier for us to integrate anyway. So what would 5x times x to the negative 3rd be? What is the exponent on the x, even though I don't see it? It's a 1, isn't it? And so if I'm multiplying an x to the 1st times an x to the negative 3rd, what am I going to get? I add those exponents, and 1 plus negative 3 would be x to the negative 2 power, wouldn't it? So far, we okay? Plus, what is going to be my second term? 3x to the negative 3 power. Are we ready to integrate now? Yes, we are. So let's go term by term. So if I'm integrating, I know the 5 can kick out. And how do I integrate x to the negative 2 power? I'm supposed to do what to the exponent? Add 1. So what is negative 2 plus 1? Negative 1. And then I need to do what else? Once I get the new exponent, I have to do what with it? Divide. Good. Divide by a negative 1. All right, that's going to be my first term. I'll clean it up in a minute. Plus, let's see if we can integrate 3x to the negative 3 power. Keep the 3, and then we said we add 1 to the exponent when we're integrating. So what is a negative 3 plus 1? That is correct. So 3x to the negative 2 power, but also do what? Divide by a negative 2, and then we know we're going to need a plus c on the end. Now, we got to do a little cleanup. I've got a positive 5 on top, divided by a negative 1 on bottom. What's that going to turn into sign-wise? negative 5, and then I can leave it as x to the negative 1, or I can put the x in the denominator and give it a positive 1 as an exponent. Perfectly okay, either way. And then on the second term, I've got a positive 3 on top, negative 2 on bottom. So I could write that as minus the fraction 3 over 2. And where will the x to the negative 2 end up if I write it with a positive exponent? On the bottom. So I would have an x squared on the bottom and a plus c. Right? And then again, we could go through and differentiate and see if it gives us back what we started with. Now, I do want to mention something to you, because this is going to be one of the things when you start off with a fraction, you may not recognize right off the top of your head if it matches whenever you do the differentiation. So let me just kind of show you. If we were going to take this and differentiate it, we would have, okay, let me, actually I don't want to put the prime there yet because I'm going to rewrite this so that we have negative 5 x to the negative 1 minus 3 halves x to the negative 2. And now let's differentiate, okay? So what would negative 5x to the negative 1 be when you differentiate? It'll be a positive 5, because negative 1 times negative 5 gives you a positive 5. X to the, what's my new exponent? Negative 2. That's going to be our 5 over x squared when it's cleaned up. Now, this term, if we pull down the negative 2 and we multiply it times the negative 3 halves that's already there, and we take one away from the exponent, we're going to have x to the negative 3rd power. Now, this negative 3 over 2 times negative 2 over 1, multiplied together, that turns into what sign? It's a positive. The 2's are going to cancel, and I'm going to get 3 over x to the 3rd. Does that make sense? As far as how, now, that does not look exactly like what we started with, because if you remember, what we started with looked like that. But here's what you need to realize. This was put together as a single fraction. It meant we would need a common denominator. We do not yet have a common denominator. What would need to be the common denominator if we were going to write it as a single fraction? I've got an x squared in one denominator and x to the 3rd in the other. What would be my common denominator? X to the 3rd. I've got to pick the one that has the larger exponent. That means this second fraction is fine. What would I have to multiply the first fraction by? X squared times what gives you x to the 3rd? X. So if I multiply the first fraction by x on bottom, wouldn't I also have to multiply by an x on top? That would give me the common denominator, and this thing would turn into 5x plus 3 on top over x to the 3rd on the bottom, which is what we started with. Okay? You have to do a little algebra manipulation if you're going to double check by taking your derivative, but we were able to show we did it correctly. Okay? Now, the next one does have something in it we haven't seen. In any of our examples, that's the e to the x. I would say let's go ahead and clean this thing up before we start, because we definitely don't want to keep the fractions. So we've got 5x to the 5th plus 3x to the 6th e to the x. And we're going to multiply that by what? So we can get rid of the fraction. What do you multiply by? X to the negative 6th power. So if I do that, let's rewrite it. We haven't integrated yet, so keep your integral symbol. And what would an x to the 5th times an x to the negative 6th be? 5 times x to the what? Negative 1. plus, what happens here if I multiply 3 times x to the 6 times e to the x times x to the negative 6? What happens to, what does x to the 6 times x to the negative 6 end up being? X to the 0, which is 1. In other words, they would cancel out, and I would be left with 3e to the x. That is what I want to integrate. Now, so far are we okay? Looking at the first term, do you recognize something we better pay attention to? What is our exponent? Okay, the problem is when there's a negative 1, I can't use that rule for integrating when I have x to a power. Because remember, if I add 1, it turns the exponent into 0. So we're going to think of this as 5 times 1 over x. Okay, and I'm going to rewrite it that way. So that now when we integrate, this is going to turn into what? 5 times, what do you get if you integrate 1 over x? There you go, natural log of the absolute value of x. Now we're ready to integrate the second term. I see a 3. So I keep it. That's my constant multiple. How do you integrate e to the x? It's just what? And then we need our plus c. And we could double check that one, but there's really no need. Okay, one more example I'm going to show you. This one is explaining how we could actually find the specific function that would have this point on it. Here's the extra thing that they've given us. We have, our function is 8x to the third plus 9x squared plus 2. And then it has this point. It says r of 1 equals 16. Remember, this is my x value in an ordered pair. This is my y value in an ordered pair. So in other words, I've got this that would be the derivative. I can integrate it and come up with that family of functions, the one that has the plus c on the end. There's only going to be one of those functions that actually has this point on it. We're going to be able to find it because we know a point that's on the graph. So here's how we do it. Let's start off just like we have been. We need the indefinite integral of 8x to the third plus 9x squared plus 2. And we need a dx. Now, let's see if you can integrate this thing for me. What's going to be the first term when you integrate it? 8x to the third becomes, tell me what to write down. Do I keep the 8? Always. And then x to the third is going to become? Good. X to the fourth, because I have to add 1 to the exponent and then divide by the new exponent. So that's going to be over 4. Plus, now let's integrate the next term. I write down the 9. How do I integrate x squared? It becomes x to the third over 3. Good. And we'll clean all this up in just a second. And then, bless you, how do you integrate 2? 2x. Good job. And then I know I have the plus c after. Now, if I clean this thing up, I can reduce down. 8 over 4 becomes 2. So I have 2x to the fourth plus, what's my next term? 3x to the third plus 2x plus c. Okay, we're going to take that to the next page. This one is explaining how, goodness, oh, actually, let me go. And here's what we're going to do with it. We're going to find what c would have to be for this thing to have that point that they gave us. So I'm going to take my function, and since they used an r, I'm going to say r of x is equal to, and the function we came up with was 2x to the fourth plus 3x to the third plus 2x plus c, right? And here was the information that they gave us just a moment ago. that we haven't used yet, that was that r of 1 was equal to 16. Okay? Now here's what that means, is that 1 would be an x value. So I'm going to put 1 everywhere I have x in this function, and then my y value would be 16. Does that make sense? That's an algebra thing. So this is my x, this is my y. So if I put in 1 everywhere I have an x, and I still don't know what c is, that's what I'm trying to figure out, is what would be c. What would I put in place of r of x? 16. You got it. So let's clean this up now. 16 will equal, what's 2 times 1 to the 4th? 2. Plus, what's 3 times 1 to the 3rd? 3. Plus 2 times 1 is 2. Plus c. Well, 2 plus 3 is 5. 5 plus 2 is 7. If 16 is equal to 7 plus c, what would c equal? Because I would subtract 7 from both sides, and I would get c is equal to 9. Here's what that tells me. If I go back to this line right here, I'm going to know the exact function that would have that point on it. It would be 2x to the 4th plus 3x cubed plus 2x, and instead of putting a plus c, I'd put a what? Plus 9.